Hello everyone. This is the third and arguably one of the most important lectures that I'm going to present on the topic of circuit analysis, and therefore it requires your attention. We're going to describe an algorithm that we can then use to analyze circuits, and this is a very general approach to circuit analysis as a problem. In other words, it's a very general problem-solving technique that hopefully by the end of this lecture you're going to understand the basics of it. But we're going to practice the same technique over and over throughout the semester in the face-to-face sessions and hopefully get a good handle of how to do circuit analysis. So let's just do a quick recap of what we mentioned before about the most important parameters in circuit analysis. We have the voltage that we define as energy per unit of charge, and then we have current that we define as charge passing through a cross section per unit of time. And then based on this definition, power simply became voltage across a component multiplied by the current passing through the component. And physically speaking, the current is basically charge carriers that move through a material as a result of a force that is applied. So if this is a piece of material, and there are obviously atoms in this piece of material that are made of a nuclei that is positively charged and electrons that are negatively charged around it. And under a certain condition that is not really the topic of discussion in this class, these electrons, some of these electrons, they actually can move given a force, electrostatic force, is applied to them. So if we can actually generate an imbalance in the energy that is across this material, there would be a force, electrostatic force, applied to these charge carriers, and then therefore the electrons can move. You can think of this as having a ball sitting on a flat surface, and then if I create an imbalance, and on this flat surface the potential gravitational energy is the same everywhere, and therefore there's no gravitational force applied, no net gravitational force applied to this ball, and the ball is not going to move. Now if I change this situation by slightly tilting the surface, now obviously the potential energy on this, the potential gravitational energy on this end of this surface is higher than the potential energy, gravitational energy on the other end, and you will get therefore a net force applied to the ball, and the ball can roll down. So with the same, you can use the same analogy. Obviously an electron is not a ball, but this analogy helps you understand how relevant or how similar these two systems are once you think of this in terms of energy. So if there's no potential difference, electrical potential difference, here was a gravitational potential, here we have electrical potential. If the electrical potential on both sides are the same, there is no net force applied to the electrons, and there is no net movement of the electrons. Now if you somehow create an imbalance in the potential energy, electrical potential energy, that is on the two sides, by how we say that is by applying a voltage across. Why? Because the voltage is derivative of energy with respect to unit of charge with respect to charge. Therefore, when I say the voltage on one side is higher than the voltage on the other side, it means the energy on one side is higher than the energy on the other side. Same here, right? So if I apply a voltage difference here, it's as if I'm tilting the electric potential frame or surface here, and by doing that, then the electrons are going to be exposed to a net electric force, and therefore they can, in some cases when we are dealing with conductive material, they can then roll down and start moving. So in these devices, as a result of application, these kind of situations, as a result of application of a potential difference where you have a voltage applied between the two ends, and we can actually call this end a V plus and a V minus, and we define V being equal to V plus minus V minus, the potential difference, then you would, as a result, get a current passing through. Now, what this means is that by the convention that we're using, there would be a current going from the higher electrical potential to the lower electrical potential. So there would be a current passing. But this actually means that the electrons in this system are moving from the lower potential toward the higher potential. So the electric field, so this is the field inside, would be like that, and the electrons move in the reverse direction. This is the convention that we're using. Okay, and now with this component, with the situation that we have, what's important for us is to understand how much power or energy is being consumed in this device, if this is a device that is consuming the electrical power. And that's simply taking the voltage across and multiplying by the current that is passing through it, and you get the power. Now, you have to keep in mind that this voltage that you apply across and the current that is passing through are not necessarily constant. So in that case, then you are not necessarily dealing with a simple calculation of multiplying two constants by each other and getting a constant power. Each one of these could be basically functions of time. So in that case, your power would be a function of time changing as the time passes, because the voltage that you're applying across the two components are changing and the currents that are passing through are changing. And in this case, if you happen to need to calculate the energy, since power we know, and I'm going to write that down here, since power we know is derivative of energy with respect to time, then if you have a changing power, and if you need to calculate the energy that is consumed, or for that matter generated in that component, you can simply calculate that by integrating power over time. And you may actually need to do some of these kind of time-dependent calculations in the homeworks that I assign. And if you have questions, we're going to discuss those in the face-to-face sessions. So that pretty much covers most of what we discussed the past two lectures. And now we can start moving on to the new topic, which is circuit analysis and how we do circuit analysis. So why do we do circuit analysis? We know that in order for us to be able to do useful work, we need to take the incoming energy and use the electrical components that we have to basically achieve a certain functionality. In a light bulb, for example, that was a really simple circuit and simple process where you take the energy, pass it through a device that was a light bulb, and that would give you a light. And then we also discussed that the light bulb is basically a resistor, and that heats up, and as a result of heating up to very high temperatures, you can actually get photons, light, visible light, in other words. But that's one type. In some of the devices, you actually use just a simple resistor to basically get heat. In a lot of electrical ovens, that's the case. So heat might actually be what you're looking for in an electrical device. But there are other much more complicated functions that we now take advantage of by connecting these electrical devices, where in most of them heat is actually not what you're looking for and instead is a waste of energy. Any of the electronic devices that you have on you, like your cell phones, would be examples of that, where heating up is not the useful work that you're looking for. All that said, we take these individual components, electrical components, and then connect them to each other in a network. And they will eventually, if you're doing a proper job of designing the network, they're going to give us a functionality that we're looking for. So if this is A, B, C, D, E, each one of these could be a different component. And now what's important for us in circuit analysis, and the reason why we are interested or why we do circuit analysis, is that we would like to know how energy that is injected into the system through a mechanism by one of these components that is sourcing the energy out, how is it distributed between all these different components, and how is it consumed or stored, and that's the ultimate goal. And for that, we know that we defined only two parameters of interest. One of them is a voltage, and the other one is a constant, electrical potential and electrical current. So in other words, if I can calculate the voltages across, or the voltages of each one of the ends of these components, and then the currents that are passing through, then basically I can calculate everything there is to be known about the energy distribution and transfer of energy in this system. Voltages multiplied by the voltages across multiplied by the current passing through are the powers. So circuit analysis basically is a process through which you calculate all the voltages and currents in a network of electrical components. I'm going to write that down. So circuit analysis. This is the goal. This is what we are trying to do, which is basically calculating all the voltages across and currents through electrical components in a network. So in this simple case, if I take all the ends of these components, and actually I'm going to call them something. I'm going to call these ends of these components nodes from now on. So, and each end, which is basically a terminal or connection to that electrical component, and by the way, in parentheses, in this specific case, these components each have two terminals, but that's not necessarily the case for all the electrical devices. There are certain electronic devices that have more than two terminals connected to them. But nevertheless, each one of the connections to the electronic device where the current can actually pass through is called a node. So this is a node, and this is again a node. That's a node. That's a node. This is a node, and they're electrically connected to each other using what we call really good conductors. And we're going to get there why that matters and what kind of assumptions are we making there. Okay, so now this is obviously a symbolic representation of what reality is. For example, this could be just a battery, and these could be light bulbs or heaters or anything, resistors, capacitors, inductors, diodes, anything that you can think of, any electronic component. And they're connected with really good conductive wires. Now, one could imagine that in this situation, if my assumption is that this between the two nodes there is a wire with very high conductivity, meaning that there is no loss of electrical energy when the electrons pass through, then something interesting could be assumed here. I can assume that these two nodes are actually electrically the same. So I can combine these nodes with each other. So before I get there, I have to actually branch off and explain what I mean by high conductivity or small resistivity. So here's a definition that we're going to have to use from now on for an electrical component that passes current with a certain resistance. So if I have a voltage difference across, and I have a current that is passing through, different material, if you make them into the same size and apply the same voltage difference, potential difference across, they would end up passing different amount of current. So because of that, we have to quantify this so that we can compare and basically do models and do analysis based on that quantity. This quantity is, for this piece of material, is called resistance, and it's shown with a symbol R. And the way that is defined is by taking the voltage difference, higher potential minus the lower potential, and then divided by the current that is passing through it. So this is how we define electrical resistance. This relationship, assuming that this value is a constant resistance, resembles a very linear dependency between the voltage and current, meaning that if you double the voltage difference that you apply across the component, assuming that the resistance of the material is constant, would mean that you get double the current that is passing through the device. And with that assumption, this equation sometimes is called the Ohm's law, and it's written actually in this form. So the constant resistance multiplied by the current that is passing through is equal to the voltage difference across the component. So a lot of times this is called the Ohm's law. One thing that I want to make sure that you realize is that the current that is passing through multiplied by resistance is equal to the voltage or potential difference across. And this is a concept that a lot of times get confused with the voltage that is shown like that. So if you show the potential of each node, you actually have to take the difference, and then that's equal to this multiplication of the resistance by the current. But if you show the voltage as the difference, meaning that if you assume that the higher potential minus the lower potential, you define it as the voltage across, or V, then you can show it as V equal to Ri. Again, I think I mentioned this before. Sometimes this confusion happens where people assume that this V is actually the voltage on one end. That's not true. This V voltage across is the potential on one end minus the potential on the other end. This is a very critical concept that a lot of times gets confused, and you need to correct that if you're one of the people that have that misunderstanding. Okay, so now this resistance, this quantity, has a really valuable application, because now I can basically compare material in terms of their resistance against passage of current. In other words, this value is quantifying how much current do I get for the same unit voltage that is applied across the material. And if you are looking for more current passing through, then you need to reduce the resistance. If you're, for whatever reason, looking for lower current to pass through, then you have to increase the resistance of the material that you use by choosing a different kind of material or by choosing a different geometry, because this resistance is actually both a function of the material property that is used here, and also it's a function of the geometry. And we can quickly discuss how that is. But for example, you know most likely that a lot of metals have low resistance, but in the same metal, for example, if you take a certain cross-section of the material, so if this is the cross-section of the copper wire that you use, and then you've compared that to this smaller cross-section of the same copper material, the resistance that you get out of this is more than the resistance that you get out of this. And that kind of should be intuitive to you, because here in each cross-section there are a lot more charge carriers, and therefore when you apply a force, there's a lot more of these charge carriers that can pass through the cross-section. So obviously the amount of current that you get becomes pretty much proportional to the cross-sectional area. So the higher the cross-section, the more current. So therefore the resistance of your piece becomes inversely proportional to the cross-section. So the resistance, we know therefore that is inversely proportional to the cross-section, area of the cross-section. And you can actually think about other ways to relate the resistance to the geometry. This was just an example to show you that the resistance is both a function of geometry and also the material. And obviously the same size, if you take the same size wire, and this one is aluminum, this one is copper, then this one is going to, because of the difference in the material property, this one is going to be the lower resistance, and aluminum is a slightly higher resistance, although both of them are pretty good conductors. So resistance is both a function of material property and the geometry. Okay, so with this definition, the reason I discussed this is that I needed to tell you how we're going to deal with these connections, right? Because these connections are going to be assumed to be ideal. What does that mean? That means that when I take a component here and I want to connect it to a different component, in between I'm going to use a piece of wire with a really good electrical conductivity. In other words, what I'm going to assume from now on is that the resistance associated with this piece of wire here is negligible compared to the resistance of the actual components that are in the circuit. And that's a very important assumption that we're going to have to make in order to simplify the analysis. If that's not the case, if basically the resistance, because every piece of these wires in actuality, they do have some finite amount of resistance. But if the resistance is negligible, then I can completely ignore it. If it's not negligible, then I actually have to take this piece of wire, replace it with a box, and say, okay, this is actually a component in my circuit that has a certain resistivity. And if I'm not doing that, if I'm showing you a circuit like this, what I'm telling you is that this piece of wire that connects the components to each other has a resistance that is negligible, close to zero, compared to the resistivities of the components that I have considered. So what does this mean? If I put R equal to 0 across this piece of wire, which you can imagine it's a component, what I'm saying is that the voltage on one end minus the voltage on the other end divided by the current that is passing through it is equal to 0 for that component. So in other words, if this is true, then what that means is that the voltage of one end and the voltage at the other end are actually equal to each other. Okay, so if I want to define a potential for this node right at the end of this component, and a potential for this node right at the end of the other component, and call it V1 and V2, if R, the resistance of this piece of wire in between, is equal to 0, I can simply assume that these two potentials are the same. So, in other words, what I can do is to say that these two nodes are actually one node. And if I want to name this node anything and assign a potential to it, I can actually use one potential for both. Okay? So, a very important discussion. So, with this, I am going to quickly identify all the nodes in the circuit. So, we have one node here, one node there, one node here, and one node there. So this circuit has 1, 2, 3, 4. These two nodes are combination of two different nodes that are connected with wires with a resistance of almost 0. Okay, so with this, I'm going to stop this lecture and give you some time to think about the discussions that we had so far, and then continue this same discussion in the next lecture that you're going to watch. Thank you.